In the last class, we learned about cyclic prefix and why do we need cyclic prefix, what is the advantage of cyclic prefix. Today, we'll see how the reception of OFDM signal is done and also what are the different types, different ways in which you can process the signal after signal reception. So this figure is from the textbook of Andrea Goldsmith, Wireless Communications. And this shows OFDM with IFFT or FFT implementation. Practically, I told you IDFT is implemented using IFFT algorithm, and DFT is implemented using FFT algorithm. So simply because it has less number of computation steps. The data comes at R bits per second, goes to a QAM modulator. It could be a QPSK modulator as well. Then this serial data is converted into parallel. So you have n number of modulated symbols here, x of 0, x of 1 up to x of n minus 1. It is a convention that you use capital letters for frequency domain. So we assume that this data is in frequency domain. After performing IFFT, you again have n symbols and these n symbols are now in time domain, and it's a convention that you use small letters for time domain signals. And this time domain data, like we said, cyclic prefix is added, and after the addition of cyclic prefix, the data is converted to serial, and then there is a discrete to analog converter. The OFDM signal, which is baseband here, is translated to bandpass by the multiplication of cos 2 pi f naught t, and you get S of t, which is the OFDM signal which is transmitted out from the antenna. So here there is a antenna section and signal gets transmitted out. And the receiver, again there is a receiver antenna. OFDM is, in this figure, it is a single input, single output technique, but it can also be extended to a multiple input, multiple output technique as well. Signal R of t is the received signal. This bandpass OFDM, it is translated back to baseband OFDM, multiplying with cos 2 pi f naught t. The low pass filter does some filtration, removes out the unwanted components, accepts the frequency range that is this OFDM signal is designed for, the bandwidth of this OFDM signal. And then there is an analog to discrete converter which samples the signal, and from this point you have discrete signal y of n. Like I told you, the mu number of symbols, mu symbols are mu symbols which belong to the cyclic prefix part, sampling of cyclic prefix. They are under inter-symbol interference, so we remove those mu symbols, and we have the rest of the signal after removal of cyclic prefix. Mu symbols is removed from the beginning, and you simply don't sample it. That's what you can do. And you have the rest of the symbols which are having interference but from the same signal itself, and the serial data is converted into parallel, and you have a number of samples here. Then an FFT is performed. So at this point you have the frequency domain x of k. This signal is x of k, where k is from 0 to n minus 1. Here you have in general x of n, where n varies from 0 to n minus 1, and addition of cyclic prefix, you have some terms, additional terms added to it, and here you transmit the signal and it is transmitted to this channel, which is a wireless channel, having an impulse response of h of n, and in frequency domain you can call it h of k. H of n can be, h of n is time domain, it can be converted to frequency domain by performing an FFT. Okay, we'll do that at the receiver side. And you have h of k here. Yeah. So this received signal is processed in this manner. The channel, the received signal is actually this S of t linear convolution with h of t. Okay, h of t is the impulse response in time domain, and t is for continuous variable. So here s of t is continuous in nature, so I'm using h of t also continuous in nature. However, after sampling, this nature is different. Um, it becomes discrete in nature. Okay, s of n linear convolution with h of n. After removal of cyclic prefix, you can see that the remaining part of the signal is s of n circular convolution with h of n, and by performing an FFT of this, you know that the circular convolution gets converted into a multiplication when you do FFT of this. That's a property of uh, DFT of two sequences. That is, here you have after FFT you have y of k, which is equal to x of k into h of k, where k varies from 0 to n minus 1. So h of n could be of any length. H of n could be of any length, but h of k will be having a length of 0 to n minus 1. Because you have your signal x of k getting multiplied with h of k, and x of k is endpoint sequence. So you have x of k also an endpoint sequence. And so you can see how many points FFT you need to take. You need to take an endpoint FFT. Endpoint FFT you need to take in order to convert the h of n to h of k. Another thing you can notice is that the receiver needs to have a knowledge of the channel impulse response. Only then you can write it in this way, right? You can receive it properly. Even though there are other methods, conventionally when you speak about OFDM, we will assume that the receiver has knowledge of the channel impulse response. Okay. Now there are certain problems. You would easily say that from here, from this expression, you could get x of k is equal to y of k divided by h of k. You could say that, but practically when you think about this, things are a little different. Let us see what it is. Let me just rub out all this. Okay. Practically, when you think about this, here you have the transmit antenna, here you have the receive antenna, and the signal received here will be this r of t. R of t will be equal to definitely s of t convolution h of t, and there will be some noise which will be added to this received signal. There will be some noise which I will just write as noise. Okay, some noise also will get added, and this noise is mostly this noise is assumed as an additive white Gaussian noise. Okay, additive white Gaussian noise. It is an additive white Gaussian as AWGN, which is getting added here. And this noise, it will reach the receiver, and the receiver, and it is true that low pass filter filters some amount of the noise, but along the frequency range of the signal, along the bandwidth of the whole OFDM signal, you will have this additive white Gaussian noise added to it. Even if you sample it, the noise still it will remain there. And you can see that in all the analysis, this noise also plays an integral part. Okay, noise is present in every analysis. So here you have y of n, which is in time domain, and y of n will be x of n convolution h of n circular convolution plus noise. Okay, and when you take the f of t, still there will be that noise term x of k is equal to h of k into x of k plus let me denote noise capital N. So I'm taking the when I take the FFT on both sides, I'm taking the FFT of y of n, as well as I'm taking the FFT of this RHS also. So this is x of k, h of k into x of k plus FFT of noise. So I get the frequency domain of noise. So you have plus n of k. And you can see that you started with these modulated symbols x of k, and you ended up here where y of k is equal to h of k into x of k plus n of k. So how can you get back x of k? At the receiver you have y of k only. How can you get back x of k? You can see that there are two major factors which affects x of k. One of them is h of k, which is the frequency coefficients, frequency domain coefficients of h of n, which is the impulse response. It is the it results in subcarrier fading coefficient. You could call it as subcarrier fading coefficient because it results in fading. So it is a frequency domain of the channel, and the value of that sample that gets multiplied with x of k, where k denotes the frequency domain. And there is another presence of another factor is the noise. So these two factors, they influence how you can estimate y of k. And let us see what are the practical difficulties you have in receiving the signal, and how can you overcome some of the difficulties. One of the let me just write that equation again. Y of k, which is a signal that we get after initial processing after the FFT. So we get this signal after FFT. We get this signal y of k is equal to h of k into x of k plus n of k, where this k varies from 0 to n minus 1. And how can you get back x of k from this expression? So you have y of k at the receiver, and how can you get back x of k out of it? So x of k is getting multiplied by h of k, and then it gets added with n of k. So how can you get back x of k from this? So this in general it is called subcarrier fading compensation techniques. Subcarrier fading compensation techniques. One of the method you can have is frequency equalization. This signal is in frequency domain. You can easily equalize this just by dividing with h of k. So it is y of k divided by h of k equal to h of k into x of k divided by h of k plus n of k divided by h of k. And what you get here is an estimate of x of k. So it is x cap of k. It is an estimate of x of k. So I put a cap. X of k is equal to, gets cancelled off, x of k plus the noise term n of k divided by h of k. And you can very well see that in order to do the frequency equalization, you need to have channel state information at the receiver. Only then you can compute h of k. So you have an estimate of x of k, which is not exactly equal to x of k, but there is an additional term n of k divided by h of k coming into picture. And this term n of k divided by h of k, what is the nature of that term? Mostly h of k will be having a value of less than 1 because h of k is the frequency coefficient of the channel. You can see that the channel doesn't add power to the signal. When a signal is transmitted, the channel always try to attenuate the signal. So this h of k will be normally a value which is very small. Not very small, but yeah, there are certain range of values which the channel coefficient can take, and h of k when compared to n of k, h of k will be it all depends on how the channel is going to be. But depending on the value of h of k, it can largely influence the value of x cap of k. If h of k is a small value, which means the channel coefficient is having a less value, the channel is not so good, okay? In that case, this n of k divided by h of k is going to be a large value, right? When h of k is a small value, then n of k by h of k is going to be a bigger value, which means when x of k gets added with it, then it is difficult to estimate what actually the x of k was, because x of k is getting added with a large value of noise, a large value when compared to x of k. But if x of k is an ideal value, there are, even though it cannot be a large value, a channel definitely gives some amount of attenuation to the signal. But if the attenuation is not too much, then yeah, you have the noise value which is comparatively less than when compared to the previous case. So when x of, in that case, x of k will be greater than the noise value n of k divided by h of k, and there is only small addition of a small value of noise. In that case, we can estimate x of k accurately. Okay, so when you divide with h of k, the when x of k is a small value, x of k is usually there are small values. X of k is the gain of the channel, and the channel mostly it has a gain of less than 1 because the channel doesn't add strength to the signal. Channel mostly add noise to the signal. The noise gets amplified. The noise gets amplified during frequency equalization. So that is one of the disadvantage of frequency equalization, that is the noise gets amplified when you divide with h of k. Okay, it is true that here the h of k values gets cancelled off, but when you divide the noise with h of k, the noise gets amplified, right? And why it is called frequency equalization? Because this equalization, equalization, some people might call it inverting. Okay, inverting the channel, we are actually trying to invert the effect of the channel. By inverting the effect of the channel, we actually tend to amplify the noise. Okay, that is one of the disadvantages of frequency equalization. Okay, so the frequency equalization does not fully compensate for the performance degradation due to this fading. Even though it is flat fading, this frequency equalization doesn't fully compensate for this flat fading. We try to invert the channel, but by inverting the channel, our noise gets amplified, and if the noise is having a lesser value, then we will be able to, then this again becomes part of noise. This is our noise value only. All right. So that is a disadvantage of frequency equalization, but frequency equalization is a very commonly used technique, and it works well for channels which are ideal or somewhat ideal. Second method is called pre-coding. Second method. Pre-coding needs channel state information at the transmitter. Channel state information need to be known at the transmitter. So the idea is that we are able to hear in the frequency equalization, we were equalizing at the receiver. At the receiver, when you receive the signal, we are trying to invert the effect of the channel, and we are able to get this estimate of the transmitted signal. We are trying to equalize at the receiver, but here in pre-coding, we are trying to equalize at the transmitter end. We are trying to equalize at the transmitter, and the transmitter needs to have knowledge about the channel state information. So we instead of transmitting signal x of k, you transmit x of k divided by h of k, such that at the receiver, when you have this signal x of k divided by h of k, you transmit this to the channel. And what does the channel do? The channel, this signal undergoes linear convolution, and it gets converted to circular convolution, and at the receiver, what you have is this into h of k. Okay, just like this. Here you have x of, if x of k is the transmitted signal, then at the receiver, after f of t, you have x of k into h of k. Here transmitted signal is x of k divided by h of k, so at the receiver you have x of k divided by h of k into h of k, whatever was transmitted multiplied by h of k, plus there is some noise also. What happens is here cancellation happens, because you have already compensated that at the transmitter end, and you have estimate of x cap of k as x of k plus this, what is this noise? Noise is n of k plus n of k. So you can see the advantage is that here the noise is not getting amplified. Noise, whatever was there in the channel, it is still present in the signal estimate. and you are not trying to amplify the signal. Here in this case, the value of h of k is less than 1. So you divide n of k with the value less than 1, then this noise would get amplified. But in pre-coding, you have compensated at the transmitter end, which means at the receiver end, uh, automatically this fading coefficient gets cancelled and you have the noise term added with it. Here the advantage is that the noise amplification does not happen. Noise amplification does not occur. The noise power, whatever was there in the channel, it remains the same. Even though in the frequency domain, it remains the same. So this technique is used, pre-coding is used in HDSL, wireless standard. HDSL stands for bitrate high bitrate digital subscriber lines, high bitrate DSLs. Recording is used in this. And what is the disadvantage of this? It is not power efficient because you need to compensating with a value h of k means you are trying to add more power to the signal. Alright, so h of k is a value which is less than 1. So when you do this x of k divided by h of k, we are actually adding more power to the signal. It is like you are multiplying with x of k with a value which is greater than 1, which means you are adding power to the signal. So this technique is not power efficient. It is not power efficient. It is not power efficient because the transmitter needs to spend a lot of power there. For example, channels like relay channel, for relay for the relay channel which used to have multi paths, which used to have many paths, many number of multi paths. For such channels, this technique is going to be highly inefficient because you need to compensate for a lot of channel types. So if it's a Russian channel, then there is a line of sight component. For relay channel, there will not be a line of sight component, and this method of you will need to compensate with a large value of power for this transmitted signal. Okay, so that is one of the disadvantage of the pre-coding technique. And another very obvious disadvantage of this pre-coding technique is that CSIT, channel state information, needs to be known at the transmitter end. So how does the transmitter know the channel state information? It can be known only if the receiver sends back the channel state information to the transmitter. Okay, so you need to have a two-way communication in that case. And this is difficult, and that itself will take some consume some data rate, that itself will consume some time also, that the receiver needs to send the channel state information back to the transmitter end. So it is not suitable for channels which vary fast, for rapidly varying channels. This method is not suitable for rapidly varying channels. Okay, so that is about the pre-coding technique. There is one more technique we just mentioned in the textbook, that is adaptive loading. Among these techniques, adaptive loading is considered the best technique, and we'll come to know that for this technique, CSIT, channel state information, needs to be known at the transmitter end, and we'll see how this adaptive loading is done. The idea is that when you have a channel, wireless channel, having an impulse response, say h of t, and you have your response say like this. Okay, I'm sorry, it is not h of t, it is frequency response h of f, and the axis is frequency. So you can see that at certain points, let us keep a line somewhere here. Above these points, the frequency response is pretty good. It is having higher value for channel impulse response, higher value for channel coefficient, frequency response coefficient. Along this area, somewhat okay, somewhat medium value for channel response coefficient. And below this, consider areas like this, which is having very less value, high value of attenuation for the channel channel frequency response. And when x of f gets multiplied by h of f, this low value of channel frequency response, it will have a bad impact on x of f, because first thing is, in order to compensate, you need to have this divided with h of f, which means you are multiplying this term with a large value, so you need a lot of power for that. And also you know that there is a noise term which is also getting divided with h of f, so it again results in amplification of noise. Okay, so our idea is that we'll think of how we can reduce this noise value, how we can reduce the noise value, and certain things that affect the bit error rate for any communication system. We go for finding the bit error rate. Bit error rate is like a figure of merit. It is like a figure of merit for communication systems. So we want a lower amount of bit error rate, and we'll try to find the factors that influences bit error. How do you compute the bit error rate? So you take the total number of symbols which is transmitted, and how many symbols uh, got error at the receiver. So number of symbols which had error at the receiver divided by the number of symbols which were transmitted, it gives you the symbol error rate. And if you convert that into bits, number of bits that got in error divided by number of bits that was transmitted, that will give you the bit error rate. So intention of every communication system is to lower the bit error rate, and we will think of how we can reduce the bit error rate. And one of the idea is to reduce the data rate. Okay, if you reduce the data rate, then your BER will reduce, bit error rate will reduce. Another idea is to increase the power assigned to subcarriers. Increase the power assigned to subcarriers. Increase the power of subcarriers. In that case also the bit error rate will reduce, because if x of f is having a high value of power, x of f is given a lot of power, then the noise is not going to affect less, because when compared to the power of x of f, the noise value will be less. But you see, when you have a frequency response like this, there are areas where things are really good, there are areas where things are really bad. So why don't we vary the data rate accordingly? Okay, what I'm trying to say is, when you have, how do you reduce the data rate? Data rate can be reduced by use of constellations having less size. You can see in the diagram, you have a QA modulator here, and this QA modulator It can be 2 QAM, which could be same as BPSK, or maybe 4 QAM. So using 4 symbols in the constellation, so it is almost like a QPSK. So 2 QAM could be like a BPSK, something like this. Or you could have gone for 8 QAM. So there are 8 symbols. Okay, like this. Or 16 QPSK, 16 QAM. Where you have 16 symbols in the constellation. So you see, when you have constellations of different sizes, as the number of symbols increase in a particular constellation, the difficulty in estimating the symbol also increases, right? So that is some general thing you have learned. For lower data rate, you can use a lower constellation, the constellation having less number of symbols. If you want a high data rate, you could use a constellation having more number of symbols. And coming to our problem, here when this frequency response is really good, the places where the frequency response is good, that is above this line, you could use a constellation having higher data rate. You could use a constellation having higher data rate, a higher value of constellation like 16 QAM, 64 QAM, etc., 32 QAM. And the frequency response areas where the value is less, you could use a lower data rate. So these subcarriers are modulated by QAM by using a higher order constellation. And these areas are modulated by a QAM which is having less number of symbols in a lower order constellation. Okay, it is modulated by a lower order constellation. The reason being, if you have a lower order constellation, then even with the effect of noise, it will be easier for you to estimate the symbol. And also you could have more power here. You could give more power to these subcarriers in order to have in order to invert the channel, invert the effect of the channel, and maybe a lesser power here, because the channel response is good at those points. It doesn't need more power there. So I think with this, the idea of adaptive loading is clear. So adaptive loading simply means that you vary data rate, you vary the data rate and the power assigned to each subchannel, assigned to each subchannel, assigned to each subchannel relative to its subchannel gain, relative to its subchannel gain. That's the idea behind the adaptive loading. That is, according to what is the gain of the channel, you vary the data rate and the power assigned to that subchannel. And how do you vary the data rate and power? The data rate and power, they are varied to maximize the data rate, to maximize the data rate using adaptive modulation, using adaptive modulation, such as variable rate, variable power. An example of an adaptive modulation technique is variable rate variable power MQAM. MQAM. So M stands for number of symbols in the constellation. Number of symbols in the constellation. Okay. So that is about adaptive loading. So let me just mention a point here. So frequency equalization is the most commonly used method. Even though there are a lot of improvisations for this frequency equalization method, and this type of a receiver which does this kind of an estimation, one name is frequency equalization. This method is called frequency equalization. It is also known as zero forcing equalization or zero forcing receiver. Zero forcing equalization or zero forcing receiver. So ZF, zero forcing equalization or zero forcing receiver. There are a number of reception techniques. The technique that gives you best reception, best estimation is ML, maximum likelihood reception. That is the best reception estimation technique. Then you have MMSE estimation, which gives you a bit error rate better than the zero forcing equalization, but due to the symbol calculation that you have here, zero forcing equalization is the most popular method among all the other methods. ML equalization, it becomes complicated as the number of symbols increases. ML equalization becomes more and more complicated. So zero forcing equalization or frequency equalization, equalizing in the frequency domain, is more popular among the signal processing engineers who does this wireless communication techniques. Okay, so that's about the different flat fading compensation techniques. Okay, and this is how mitigation of subcarrier fading is performed. Mitigation of subcarrier fading. So one method is frequency equalization, in which channel state information is required to be known by the receiver. Then you have pre-coding, where the transmitter needs to have knowledge about channel state information, and also adaptive loading, where the channel state information needs to be known at the transmitter. So the frequency equalization is the most popular, mainly because only the receiver needs to know the channel state information. Okay, that's all for today.